Okay, in this video I'm going to continue on my tutorials on thermodynamics and statistical mechanics. This is video number 37 and I'm going to discuss the Gibbs and Helmholtz free energies. I'd like to draw your attention to my website universityphysicstutorials.com. So the previous video you should watch in order to watch this, or before you watch this, is number 7, where I discussed enthalpy. So where do we start? Well, I think I'm going to start by giving you a bottom line up front, or the bottom line up front, or the bluff. The bottom line up front. Okay, so I tell you my bluff today, not the best acronym, but anyway, my bluff is as follows: that when we say free energy, when we say free energy, what we mean is energy available for work. That's what free energy is. Full stop. Okay? Why do we have different types of free energy? Gibbs, for example, and Helmholtz free energy. Well, the reason is because it's free energy but it's at different conditions. Okay? Now, I'm going to talk about that in a moment. But that's the bottom line up front. I suppose in many respects you could stop watching now. The Gibbs and Helmholtz free energies are the energy available for work when you destroy a system or when you annihilate a system, and the reason they're different is because they're the free energies, or the energies available for work at different conditions. So where do we go from here? Well, let's think about doing an experiment. Okay, so and let's think about the thermodynamic quantities. The normal thermodynamic quantities are pressure, temperature and volume. Okay, you might also have the number of particles. Alright? So think about something which is at constant pressure. So think about an open container, for example. Let's say you go into your chemistry lab and you have an open container. Now, atmospheric pressure is here, it's here, it's here, and it's here. So the pressure of your system is constant. Okay, this is when it's an open container. So when you do something, it's going to be at a constant pressure. Now you'll see in a minute where you might not have constant pressure. And generally we have things at constant temperature because, well, if you have your container in the middle of the laboratory, well, it's going to have constant pressure because the atmospheric pressure is there. But most likely it's also going to have constant temperature. And the reason it's most likely also going to have constant temperature is because it's in thermal equilibrium with its surrounding. It's at room temperature. So in a chemistry lab, for example, more often than not you have constant pressure and constant temperature. Okay, so that's where we need to start. So I suppose constant pressure is different to having constant volume. So let's say this time we have once again we start with our open container, except this time I close it. Okay, so I put a roof or a cap on my container. Now, this time, while the pressure on the outside, namely atmospheric pressure for inside our chemistry lab, is still the same, the pressure in here is not constant, and I'll explain why in a moment. But what is constant is the volume. Okay, let's say that the volume is constant. And as I said earlier on, usually we say the temperature is constant. Okay? And we'll talk about a situation in a moment where the temperature may not be constant. Now, let's say that in my little container, let's say in my container let's say I have an open container. Go back to my open container, right? So I have my open container like this, and my open container is filled with particles, right? Like that. And I pick up one more particle and I put it in there. But the system is at constant pressure with the atmosphere. So when you add a single particle, you're adding volume, so the volume goes up but the pressure is still constant. So when you add particles, you don't change the pressure, however you do change the volume. Now, think about this one here on the right hand side where we have a closed container. Let's say that somehow I'm able to teleport a particle into this container. So here's my container. It's filled with particles. Let's say gas molecules, doesn't really matter. And let's say somehow I'm able to teleport another in there straight through the barrier of the container. Okay? Well, this time the difference is this time is that if it's a constant volume, then by definition you can't make room for any more particles or energy or matter. Okay? Thus, if something is a constant volume, we're not concerned, we're only concerned, with the internal energy of the system and the temperature. So we don't think about the volume. But if we add an extra particle, we automatically increase the temperature, or the pressure. If you increase the number of particles, you increase the pressure if it's a constant volume. And if you decrease the number of particles when a constant volume, you're also going to decrease the pressure. Okay? And the final one is, well, why is this constant temperature thing so important? Let's think of a piston. Okay, so in your engine, for example. So let's say there's my container, and here's my piston. Okay, there's my piston, and I have an arm on it, so I can move my piston. So inside here, let's say we have our gas particles. Let's say we have 4 gas particles, and I want to increase the pressure, but I want to keep it at constant temperature. So I want T constant, pressure I want to go up. Okay, so we know that PV is equal to nRT. So in order to increase the pressure, I must decrease the volume. But the important point here is we're trying to keep the temperature constant. So of course, I don't want to really insult your intelligence, but I think this is important. So we compress the gas by moving the piston to the left as you look. But by increasing the pressure, or by decreasing the volume, what we're actually doing is we're increasing the temperature. So PV is equal to nRT. So we're actually going to be increasing the temperature. So what we need to do here is we need to suck out some temperature. We need to let temperature flow out. So because the gas is going to heat up as you compress it. So what we need to do is let some heat flow out. Now that's to keep it at constant temperature. Now conversely, if this time I let the gas expand like this, so this time the gas is going to get colder as, we'll say, I expand it. So in order to keep it constant temperature, I need to this time add heat. Okay, so there's going to be, well, say a Q is going to be a heat flowing in or flowing out. So that's what constant temperature means. Constant temperature usually implies that you're either going to be adding or subtracting heat during the process. Okay, that's a good bit of revision. So let's start. So the enthalpy, which we give the placeholder H, we said in a previous video that's going to be the internal energy, we'll say, of the particles, plus it's also going to be PV, U plus PV. So we say that PV is the work done on the atmosphere to make room for the particle. Okay? Now, the important point here is that we're at constant pressure. So constant pressure. Okay? So this is so PV is the work done on the atmosphere in order to make room for the particle. Just to remind you, if something is at constant pressure, then adding to the system will not change the pressure, but its volume will change. Okay, so we define the enthalpy as H is equal to U plus PV. Okay, let's move on. So the first free energy I'm going to discuss is the Helmholtz free energy. So Helmholtz, we give the placeholder F. Helmholtz free energy. Now, what's the important point about Helmholtz free energy? Well, Helmholtz free energy is at constant temperature, and it's also at constant volume. Okay, so remember from earlier on, we can accept that having something in constant volume is different to having something in constant pressure. Alright, So let's see what the energy available for work is. So if we annihilate our system, how much work can we achieve using this particular system? So if the environment is a constant temperature, then when our system is not hot, when our system is not hotter than its environment, energy can flow from the environment into the system. So what this means is that the energy cost to us is reduced. So let's say here is my system, and say it's at, I'm going to draw a big T for it's hot, and I want to make my own. So this is the environment in black, and here's my system in green, but this is a small t. So because our environment is a constant temperature, when we make our system, namely a particle in this case, some heat can flow. So some heat flows naturally from our environment into our system, and this reduces our energy cost. And this is only possible because the environment is a constant temperature. Of course, it assumes that our environment is going to be hotter than our particle is now. But anyway, our particle is going to be. Now next, if something is a constant volume, then by definition you cannot make room when you add energy or matter to it. Thus we are only concerned with the internal energy of the system. So that means the free energy available for work when you're at constant volume and constant temperature is the Helmholtz free energy, and we define F is equal to U minus Ts. So this is the energy, this is the internal energy, or the energy required to make our system. But because we're at constant temperature, we're able to get free energy, I suppose, from our environment, and this reduces our energy cost. So this is from environment. So in actual fact, it's cheaper to make our system if we put it into an environment at constant temperature and constant volume. That's my Helmholtz free energy. So next we're going to consider our Gibbs free energy. Gibbs. Now, of course, we need to define what the parameters are when we're talking about Gibbs free energy. This time we're going to be talking about constant pressure and constant temperature. Alright, so we're talking about constant pressure and constant temperature. This is our Gibbs free energy. Now, if we account for making room for our particle, say where the environment is at constant temperature, we can reduce our energy cost from our enthalpy by Ts. So this time, this is pretty much the same as enthalpy. However, because we're at constant temperature, in the same way as with the Helmholtz free energy, where we got this Ts term. Okay, we can now reduce basically our energy cost this time again. So we say that G is equal to U, we say it's U plus PV minus Ts. This is our Gibbs free energy. Now you might be saying to yourself, what is this Ts term that I've mentioned? I've just kind of thrown it out there. So I'll talk about that in a moment, but essentially what we're saying is there is an amount of heat can flow into your system which is equal to which is at maximum, we'll say it's less than or equal to the amount of the temperature of your environment, or excuse me, the temperature which your system becomes, and this entropy, the entropy of your system. So if you create a system with high entropy, you're able to put in more heat from its environment. I think you should just accept that. So a system which has more entropy will be allowed to receive more energy as heat from its environment. So in order to make a system, we must either input the enthalpy H, the Helmholtz free energy F, or the Gibbs free energy G. Conversely, if we want to use our system in order to make work or do work, we destroy it and get out F, we destroy it or get out G, or we destroy it and get out H. So that's why we say it's the energy available for work. Okay, so what's next? Next, I want to look at why or who uses which, we'll say. Now think about it. I said in a chemistry lab, chemists will say, chemists usually operate at, excuse me, that's an at rather than, supposed to be an at rather than an and. They usually operate at constant pressure, okay, and constant temperature, T and P constant. So for that reason, chemists usually use, that's supposed to be use, G. So chemists usually use the Gibbs free energy because it happens to suit the situation of the parameters with which they're operating. However, physicists usually use the Helmholtz free energy because they're talking about constant temperature and constant volume, where these guys are talking about constant temperature and constant pressure. Okay, so, but the main thing, or the problem here is we ever only get the total Helmholtz Gibbs free energy or enthalpy back when we fully annihilate our system. But this rarely happens. Okay? So usually what we actually examine is the change in the Gibbs, or excuse me, the change in the enthalpy, the change in the Gibbs free energy, the change in the Helmholtz and the change in the Gibbs. Because it's rare that we actually destroy or annihilate our system. So we usually just look at the changes when we're analyzing what's going on. So we need to look at the changes of our enthalpy, our Helmholtz free energy and our Gibbs free energy. So if we look at our enthalpy, H is equal to U plus PV. Well then, it's a constant pressure, okay? So for that reason, delta H, the change in the enthalpy, is going to be delta U plus P delta V. Of course, because it's at constant pressure. So then let's look at our Helmholtz free energy. So this time F is equal to U minus T times S. Well, the Helmholtz free energy is a constant temperature, but it's also at constant volume. So that means in order to get the change, what we're really looking at, that means that delta F is going to be delta U minus T delta S. And of course, we'll say delta U is the first law, it's going to be Q plus W. Where this, we define the, this is positive if there's heat in, and this is positive if there's work done on the system. Okay? So that's by definition, that's why we use plus, is if we define Q and W like that. And finally, let's look at our Gibbs free energy, or our change in the Gibbs free energy. So we know that G is equal to U plus PV minus TS. Okay? So if we look at the change of this, we're talking about constant pressure and constant temperature. So we're going to get delta G is equal to delta U plus P delta V minus T delta S. That is our change in our Gibbs free energy. Alright, so actually I think it's now time to look at it perhaps another way. I'll just read out some text here, okay? So if we look at our Helmholtz free energy, this is the total energy needed in order to create the system minus the heat term you get for free from the environment at temperature T. And the Gibbs free energy, this is just the system's energy minus the heat term that's in F, or the Helmholtz free energy, okay, plus the atmospheric work term that's in the enthalpy. Okay, and finally we can think about the enthalpy. This is the system's total energy you would need in order to create the system out of nothing and put it in such an environment, or put it in any environment. Now, there are one or two more things I'd like to show you. So if we think about, we spoke about the different changes, okay, and we know that the first law says delta U is equal to Q plus W, and I spoke about how we define that. So W, the work done, is positive if it's done on the system, and Q is positive if heat goes in. But if we look at delta F, so delta F is equal to Q plus W minus T delta S. Okay, because I just subbed in our what did I sub in? I subbed in the first law, of course. Now note that if we're lucky enough to create any new entropy, okay, so this was supposed to be delta here, or excuse me, if we're lucky enough not to create any new entropy, so let's say delta S is equal to 0. So in making our system, we didn't increase the entropy of the world, okay, then the heat must be equal to T delta S. So if this is the case, Q is equal to T times delta S. That's if we're lucky enough not to create any new entropy. And that means that delta F is just equal to the work done on the system. Okay? So all of our input work can later be used as part of the Helmholtz free energy. However, when new entropy is created by making our system, then the heat, we'll say, is going to be less than T delta S, and that means the change in the Gibbs free energy is going to be less than or equal to the work done on the system. Okay, so if we apply this logic, or similar logic, excuse me, to the change in the Gibbs free energy, delta G. So delta G is Q plus W if we sub in the first law, plus P delta V minus T delta S. Okay, now applying the same logic as the last time, we saw that Q is less than or equal to T delta S, or Q minus T delta S is going to be less than or equal to 0. Okay, that means that delta G is going to be less than or equal to the work done on the system plus P delta V. Okay, you might be saying, well, where am I going? Who cares? What's the significance of this? However, because the system caused the environment to expand, we know that the system is doing work. So the work is minus P delta V on the environment. Okay? So we'll say that's the work on the environment, or the mechanical work done on the environment. But we may also have other work. I don't know, we may have electrical work or whatever it is. Okay, so W other. So that means that term W is equal, W plus P delta V becomes minus P delta V, this term here. It becomes plus W other, but we also have this P delta V up here. So the point here is the P delta V's cancel, and that our change in Gibbs free energy is going to be less than or equal to the other work done on the system, W other. Alright, W other. So I think that's pretty much all I've got to say about that. So I hope that was insightful. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also visit universityphysicstutorials.com.